Welcome back to CS Connect series. Under set theory, we are going to see about a small topic on computer representation. How will we represent set elements in system? This is what we are going to discuss in this video. How do we actually store sets in system? There are various ways to represent sets using a computer. One way is to store in an unordered fashion. Usually set elements are not ordered. So if you have a set with elements 1, 3 and 5, it can be in any order. It can be accessed as 1, 3 and 5. It can be accessed as 3, 1, 5, 3, 5, 1 or 5, 1, 3, 5, 3, 1 in any order. The other way to store sets will be store in arbitrary order. We'll just try to understand in what way one method is better than the other. Union, intersection or difference of two sets would be time consuming. Why? Because this requires a large amount of searching for elements. When they are unordered, you don't know which element is present in which position. Think in the context of a computer. Only when you know a particular location, you will be able to access a particular element. If you are not able to trace out where it is, this will in turn require a large amount of searching for those elements. After searching them only, you will be able to do union intersection. So when you have two sets A and B, you have to search for the first element in A, then search for the second element in A. Similarly, when you get to set B, you have to search whatever elements is in B, then you have to perform a union operation. Again, whatever you get in the result of union will also be stored in unordered fashion only. So this will be completely time consuming. So they have given three operations that would really take a lot of time. What about storing in arbitrary order? We are actually storing elements using an arbitrary ordering of the elements of the universal set. Why are we going for arbitrary order storage? It's because to make computing combinations of sets easy. So here they said it's time consuming, and here the reason of going for an alternative storing method is to make computations of set easy. So how are we going to represent set elements in computers? Assume that the universal set U is finite. Finite in the sense you have countable number of elements. Say for example, let's take 1 to 10. The number of elements of U will not be greater than or equal to memory size of the computer being used. So whenever we consider the computer memory, usually the number of elements will be quite less than that. That's what they are represented as not greater than or equal to. When they say not greater than or equal to, this will in fact mean it is less than. So the number of elements in U will be less than the memory size is what they say. Since they have given the set as finite set, they are just comparing the number of elements to the memory size of the computer. Specify an arbitrary ordering of the elements of U, for instance A1, A2 and AN. So let's take universal set 1, 2, 3, 4, 5. So this will be A1, A2, A3, A4 and A5. If you have another universal set U is equal to 2, 4, 6, 8, 10, then here also it will be A1, A2, A3, A4 and A5. This ordering will say which element is actually occurring first and which element is actually occurring next. Why are we giving this kind of arbitrary ordering? When you are going to perform set operations or set related computations in computer, you have to know whether a particular element is present or not. So let's take universal set to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's take a subset A. Let's take this A to be 1, 2, 3, 4, 5. Represent a subset A of U with the bit string of length n. So how will we actually represent? Just take the universal set. So there are n bits here. So 1 to 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n bits means here it's a 10 bit string we can say. So which count are we considering here? We are considering the count of the universal set. We have to represent a subset A of U with the bit string of length n. This n is from this particular universal set. Now we have to use the ith bit in the string to denote 1 if A of I belongs to A. Now we have this to be A1, A2, A3, A4, A5, A6, A7, A8, A9 and A10. Now let's take ith bit. So A1. Do we have element 1 in A? Yes, we have. So this particular position will have bit 1. So let's take 2, it is present. Let's take 3, it is present. Let's take 4, it is present. Let's take 5, it is present. The set A is done now. Now what about an element if it is not present in A? Let's take this 6 element. This element is not present in A. So what do we represent here? It is a 0. Do we have 7 in A? We have a 0 here. Do we have 8 in A? No. Do we have 9 in A? No. Do we have 10 in A? No. So this will be the bit string of length 10 that will represent subset A of U. So this kind of ordering is what they say as arbitrary ordering. Now let's take an example here. Let U is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The example that we saw just now. And the ordering of elements of U has the elements in increasing order, that is AI is equal to I. So what is this AI? This is A1, A2, A3, A4, A5, A6, A7, A8, A9, A10. So when they say AI is equal to I, it is A1 is equal to 1, A2 is equal to 2, A3 is equal to 3 and it goes on till A10 is equal to 10. So this is how they are mentioned in terms of AI is equal to I. What bit strings represent the subset of all odd integers in U? Actually, what are the odd integers in U? 1, 3, 5, 7, 9. We have the universal set, the 10 elements here. So under 1, under 3, under 5, under 7 and under 9 we will have 1 bit and the 0th bit will be filled in the rest of the places. Now what is this set actually? It contains the element 1, 3, 5, 7, 9. When we mark 1, it means the element is present. When we mark 0, the element is not present. What bit strings represent the subset of all even integers in U? What are the even integers? 2, 4, 6, 8, 10. So in the same universal set, 2, 4, 6, 8 and 10 should be marked as 1. The remaining places will be marked as 0. When the system is actually looking at this particular representation, it will understand the elements are 2, 4, 6, 8 and 10. What bit strings represent the subset of integers not exceeding 5? It means it should not be greater than 5. Not greater than 5 means it should be less than or equal to 5. So let's take the universal set bit string. Less than or equal to 5 means 1, 2, 3, 4, 5. Not more than that. So we will have 0 in the other places. Now what is the set here? 1, 2, 3, 4, 5. Actually the answer for this particular question will be the representation because they are asking what bit strings represent. So when you mention this particular set of odd integers in bit strings, you have to mention as 1010, 1010. Now we will see how to do set operations in terms of this particular representation. Given a bit string for a particular set, we have to find the bit string for the complement from the given bit string. So what is the procedure? Change each 1 to a 0 and each 0 to 1 because x belongs to A if and only if x does not belong to A complement. So when we say A is equal to 1, 2, 3 in the universal set of 1 to 10, what about A complement? Anything other than A will be A complement. So from 4, 5 up to 10 we will have an A complement. So once we have 1 in the representation in A, for A complement, wherever you have 1, those places should turn to 0. The same case goes for 1 and 0 and 0 and 1. This is not for our sake, but this is how systems operate. So from the previous example, we'll pick the set of odd integers. This was the representation that we saw from the universal set. Now we have to find the complement. How do we find? We should change all 1 to 0 and then change 0 to 1. What is this set actually? This is 2, 4, 6, 8, 10. Is this the complement of this particular set? Yes, this is the complement. So when you take universal set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if 5 elements are going to be present in A, then A's complement will have the other 5 elements. So system will find the complement just by reversing the bits and then taking only those elements from the universal set representation. Now we will see about union and intersection operations. The bit strings for the set 1, 2, 3, 4, 5 and 1, 3, 5, 7, 9 are, they have given the bit strings respectively. Use bit strings to find the union and intersection of these sets. So let's take the representation. We have 5 number of ones and 5 number of zeros here. Then 1 0 1 0 in alternate places, and similarly we have 1 0 1 0 here, and we will have the universal set here. So based on this universal set only, we are actually placing this 1 and 0. Let's take this to be set A and let's take this to be set B. So what is union? It can either be present in A or in B or in both. Now let's check. 1 means the element is present. So it is present in both the sets. We are having 1 here. The second element is present only in A. That is also fine. So we are including a 1 here. The third element is present in both the sets. The fourth element is present in A set. The fifth element is present in both the sets. What about the sixth element? 0 represents the element does not belong to A here, and 0 represents the element does not belong to B here. It means when an element is absent in both the sets, it is not included in the union. So we represent a 0 here. What about seventh element? It is present in B, so we are including it. What about eighth element? We have 0 0 here, which means the element is absent in both the sets, making this to be 0. What about 9? We have in B set, so we are marking 1. What about 10? It is not present in both the sets, so we are going with 0. Now except 6, 8 and 10, all the other 7 elements will be present in the union. 1, 2, 3, 4, 5. 6 is not there, we have 7. 8 is not there, we have 9. Then 10 is not there. So this will be the union set. What about intersection? Intersection means the element must be present in both the sets. Actually just see what are the elements that is present in both the sets. 1 is present, 3 is present, 5 is present. We have 1 and 1 here. So intersection will have 1. We have 1 and 0 here. So it's not a common element. We are having 0 here. Again we have 1 and 1. So we will have 1. Then we have 1 and 0. There is no common element. We are marking it as 0. Then we have 1 and 1, which makes this to be 1 again. So let me mark it here. Then we have 0 and 0. When both the sets does not have that particular element, it cannot be taken for intersection, so it is 0. What about 0 and 1? It is present only in one set, so there is no common element. What about 0 and 0? You don't have that element. 0 and 1, there is no common element here. What about 0 and 0? The element is absent here. So the intersection operation result will be the set 1, 3, 5. Now we will get into the practice problem. Suppose that the universal set is U is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Find the set specified by the bit string 1111001111. Now what we will do is, let's take the given string in this particular format. Now we will place the universal set above it. Now you know where you have 1, so you have to just map it directly. What they have asked is find the set specified by the string. We have to find what are the elements that are present in the set. Wherever you have 1, that element is present. Wherever you have 0, that element is not present. So we know 1 is present, 2 is present, 3 is present, 4 is present. Again we have 7, 8, 9, 10. 5 and 6 alone will be missing in the sets because those positions are filled by bit 0. So this will be the set that is actually represented in this format. Next problem, what is the bit string corresponding to the difference of two sets? In the explanation part, we saw about complement, we saw about union, we saw about intersection, and here we are going to find with respect to difference operation. Given two bit strings representing two sets, represent the set of elements that are in the first set but not the second one. In the representation, if you have 1 in the first set and 0 in the second set, then that element will be selected for difference. So this is set 1, this is set 2, and this will be set 1 minus set 2. What about the other cases? 1 and 1 will have 0, 0 and 1 will have 0, 0 and 0 will also have 0 here. These three cases will give 0, but only when it is present in set 1 and absent in set 2, it will be taken for difference operation. Thus, the bit in the ith position of the bit string for the difference is 1 if the ith bit of the first string is 1 and the ith bit of the second string is 0. That is what I told you here. And it is 0 otherwise is what it is explained here. So let's take the universal set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's take it for 3, 4, 5 and then 1, 3, 6, 10. Actually, this is the question. So how do you represent 3, 4 and 5? Only under 3, 4 and 5 you will have 1. The remaining 7 positions are 0. What about 1, 3, 6, 10? Under 1, under 3, under 6 and under 10 we have 1. The remaining positions are filled with 0. Now let's go for difference operation. Wherever you have 1 in the first set, only these 3 places. Check the corresponding bits below. You have 1 in both the places. Difference should have 1 in the first string and 0 in the second string. So this condition is not occurring here. So 3 will not be included in the result. What about 4? 1 is present in the first set, 0 is present in the second set. So this element can be included in the result of the difference operation. What about 5? 1 is present in the first set and 0 is present in the second set. So this 5 also can be included in the difference set. So 3, 4, 5 difference 1, 3, 6, 10 will be this particular representation in bits. The set is 4, 5. So we have taken only these two elements for difference operation result. So this is the actual question. I did not include the question in the top part, but this is how we'll be working for difference. Next question. Show how bitwise operations on bit strings can be used to find the combination of A union D intersection B union C. A is equal to A, B, C, D, E. Set B is equal to BCD, GPTV. Set C is equal to CEIOU, XYZ. And set D is equal to DEHINOTUXY. So what is the universal set? The universal set will be the set of all the alphabets A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. All the 26 alphabets will be included in the universal set. They have given two union operation and the result of the union operation should be put under intersection operation. So this is the universal set. Let's take this to be U. So the first operation that we will take will be A union D. So how will we represent A? We have A we have B, we have C, we have D, we have E. This is A. The remaining places should be filled with 0 to say those elements are absent in the subset A. Now we will go for D. We have D, we have E, we have H, we have I, we have N, O, then we have T, U, then we have X, Y. The remaining places should be placed with 0. Now we have to find A union D. So what is A union D? The element can either belong to A or to D or to both. So wherever you have 0, 0 occurrence, it means the element is not present in A, not present in D. There alone you will have 0. The rest of the places will have 1. So let's take only 0, 0 combo here and mark them as 0. The remaining places will all have 1. 1, 0 is 1, 1, 0 is 1, 1, 0 is 1. The element is present in both the sets, in D set, in D set, in D set, in D set, in D, in D, in D and in D. We will go for the next operation, B union C. What is B? B, C, D, G, P, T. Then we have V. The remaining places are 0. What about C? C, E, I, O, U, X, Y, Z. The remaining places will be 0. Now we have to find B union C. So find 0, 0 occurrence and mark 0. The remaining places can have 1. 1, 0, 1, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1. Now we have A union D and B union C. Now if you want, we can just find what are the alphabets in A union D. So we have A, B, C, D, E. Then we have H, I. We have N, O, T, U, X, Y. What about B union C? The set will have B, C, D, E, G, I, O, P, T, U, V, X, Y, Z. So what are the intersecting point here? Just we'll see from A, B, C, D. We have B, C, D, E. Then we have I, O, T, U, then X, Y. So how many elements are there in common? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements are there in common. Let's see the intersection now. Wherever you have 1 in both these sets, you have to give 1. So 1 and 1. So we will have 1 in the first 4 places. Then we will have in this particular place. Then we have 1 here. 1 in these 2 places, 1 in these 2 places. The remaining places will have 0 with respect to intersection. So we will mark 0 in the other places. Now what are the places where we have 1? Just select. We have B, C, D, E, I. Then we have O, then T, U, then X, Y. Just count the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 elements. That's what we counted here. And I hope it is matching with whatever we marked in circle here. Now let's take the elements. B, C, D, E, I, O, T, U, X, Y. This will be the answer for this particular operation. This is just to give an idea about the representation format that is used in computers. With this, we are completing this video. I'll meet you in the next video. Thank you, viewers.